So if we want to try and represent a wave in a single equation, that means we have to be taking into account position and time. So our displacement at any given position and displacement at any given time. The way we can write this is we can say our displacement with respect to both position and time is equal to, well, it's going to be a cosine function, something sinusoidal. So we can keep our amplitude bit because the wave itself has some given amplitude. We're going to keep our cosine term. And now we're going to take into account both timing and position. So if we want the position part of our cosine argument, that's this part right here, we're looking at 2 pi x over lambda. And then we can also look at the time part. So plus 2 pi t over period. Now I'm going to go ahead and rewrite that the way your book puts it. So a cosine, and they just pull out the 2 pi and say x over lambda plus time over period. So this is a simplified version of the wave equation. In other words, it represents what's going on both in space and in time, and that's really important. So something to consider, and also the way your book puts this, is this plus or minus bit. And the plus or minus bit is simply telling you the direction of wave travel. So if you have a wave traveling forward in time, which generally speaking is to the right, well, waves are always going to travel forward in time. So if we want to talk about moving to the right, then we're talking about the negative sign here. If we're talking about the wave traveling to the left, that's where we're using the positive sign. Okay, so that's all the sign means. If it helps, really what's going on is the sign outside of a cosine function doesn't matter. So I could actually flip these around. And the idea is just like with any graph offset, if I want to shift it to the left, then I need to have a positive version here. If I want to shift it to the right, then I need to be subtracting from my equation. Okay. So there's one other really interesting piece here that we can take away from this. Remember, I said that effectively the period is the time it takes for one cycle to happen. And the wavelength is the physical length of the wave for one cycle. So if I have a traveling wave, and I know how long one cycle takes, and I know the distance one cycle takes up, I can actually figure out the velocity of the wave itself. So I know that velocity is distance over time. Well, if I say the distance for one cycle is one wavelength and the time for one cycle is a period, ta-da! This is my wave speed. Now, it may look a little prettier if this fraction bothers you, if you remember that your frequency is just equal to 1 over period. So I can also say that my wave velocity is equal to lambda times f. So my wavelength times frequency. So I'll go ahead and tell you, these are worth understanding. Here's the fun part. If I were to give you an equation, I would hope that you would be able to find the wavelength, the frequency, the period, the wave speed. If I were to give you something that maybe looked like y equals, let's say, 5 cosine of 3x plus 5t. Now, that may look a little funky, but this, if you're given this equation and you know this is the form of the wave equation, then from this you can actually find lambda, you can find t, you can find your frequency, and you can find your wave speed just from this information, as well as your amplitude. Anything that is your multiplier, this is your amplitude. This 3 is everything that's multiplied by x. Here, everything that's multiplied by x is this 2 pi over lambda. So solve for lambda. This 5 is everything that's multiplied by t. So 2 pi over period. 5 equals 2 pi over period. Solve for period. Once you have solved for lambda and for period, you can find frequency. You can find the speed of the wave. So this is actually a really powerful form of an equation. So while we're talking about characteristics of waves, let's talk about power and intensity of a wave. Now, this isn't to be confused with the amplitude. Remember, the amplitude is simply the displacement from equilibrium. That's all amplitude is about. Now, when we're dealing with power, remember that power is defined as energy per time, energy dissipated per time. And we're looking at something in terms of joules per seconds or watts. In other words, power is the rate of energy transfer. Now, power should not be confused with intensity. Now, intensity is a term that we're going to be really specific with our definition, because intensity is a term that we throw around in the vernacular all the time. Oh, that was a really intense situation, or the intensity of that heat was really killing me. Or it's something that we're familiar with in terms of vocabulary, but we need to be really specific when we're talking about intensity when we're referring to a wave. And that could be a sound wave, it could be a light wave, but when we're dealing with intensity, we represent it with the letter I, and it equals power per area. Okay, so think about your energy transfer. Is all of that energy being transferred over a small area, or is that energy being transferred over a large area? That's how we're thinking about intensity. And there aren't any special units. Power has units of watts. Area has units of meters squared. Those are our units of intensity. So there are a couple of ways that we can have energy travel. And if I'm using, say, a laser beam, where I have collimated light, so I have all of my energy, and regardless of how far away I go, I'm looking at the same area. And so what I would be looking at then is the power of the light So the energy transferred per time in this particular area. So for a laser, distance isn't going to matter. But for most other types of waves, I mean, think about the way most types of waves travel. If you drop a rock in a pond, those waves travel outwards in a circle. Or if you were to get a little more three-dimensional with it, actually in a sphere. If you think about sound waves, they emanate from a single source, but those waves travel outward like so. So I have my waves going something like this in all directions. So if my sound waves are traveling outwards in all direction, but I have to conserve energy, how do I discuss this concept? Well, that's where power and intensity comes in. Power is something that's set. It's the amount of energy that I start with and I dissipate over a given amount of time. But the power really close to my source, I still have all of that energy all in one spot, or all in a small region, a small area. But as my wave travels outward, my area gets bigger. And so I still have the same amount of energy. Again, energy is conserved, and so that energy transfer is conserved. I still have the same power, but now that power is being dissipated over a greater area. And so this is where, again, we start talking about intensity. So effectively, anytime we have a point source and waves traveling outwards, which is going to be a lot of the time, we say that effectively the area of the wave increases with distance, or increases as the wave travels. And for a spherical wave, again, and that could be like a light bulb, light coming from a lamp. It could be sound coming from a tuba. It could be a rock dropping in a pond. Anytime you have a single source and that energy is emanating in all directions, for a spherical wave, the area is simply the area of a sphere, which is going to be our 4 pi r squared. So r is our distance traveled. So it's our distance the wave travels, or the distance from the source. Okay. So if this is the area, and we say that intensity is power per area, effectively what we're saying for a spherical wave is that intensity is equal to power over 4 pi times my distance from the source squared. Now, this is an important term, because power is related to our energy. Power is going to be conserved in a sense. So, because the wave is traveling at a given velocity already. So the power isn't changing as we get bigger, but the power per area is changing. So in this case, the 4 pi is constant, the p is constant. The thing that is changing the intensity is my distance. So anytime we see 1 over r squared, we're dealing with the inverse square law. And we saw inverse square law in Physics 1 when we were dealing with Newton's universal law of gravity. But one way to think about the inverse square law is like a spray paint can. Now, matter is conserved, energy is conserved. In our spray paint analogy, we're using paint as our energy. So we're kind of flip-flopping a little bit. But if I spray my paint can real close to the board here, I may have a really dark, intense, if you will, spot. And then as I back up from the board, I still have, like, if I just do a quick spray, I still have the same amount of paint, but I have to spread that amount of paint over a larger area. And as I get further out, my spot gets bigger, but the paint gets thinner and thinner, until finally, when I'm way back here and I spray at the board, does anything necessarily show up on the board? It may not show up, but I could have someone spray paint way in the back of the room, and I can still smell it, which is to say, a little bit of that paint is still reaching me up here at the board. I may not be able to measure it, but it's not zero. That's what the inverse square law is about. Effectively, what we get is an intensity that as our distance decreases, or excuse me, as our distance increases, we fall off. We never get to zero, but we get really close. We get to a point where we can't measure anymore. So whenever we see the inverse square law, that's this 1 over r squared relationship, this is what we're talking about. So intensity is going to fall off pretty quickly as our distance increases. Now, let's talk specifically for a little bit about sound. When we talk about intensity, that's kind of a nebulous idea, because with sound we talk about loud and soft, but how do we measure it? How do we talk about the energy of sound? And it turns out sound, like light, are things that we sense as humans. It's one of our 5 senses to hear sound. Just like light, we see light. And so when we talk about light intensity and we talk about sound intensity, we have to be careful, because we can measure energy, but that's not necessarily how we perceive what we measure. So I just quickly want to kind of make you aware of the way we discuss sound in terms of how we perceive it versus how we measure it in terms of watts or joules or anything like that. So we can talk about sound in terms of loudness or intensity level. So for sound, we commonly hear people throw around the term decibel. How many decibels is it? And that's kind of how we determine how loud it is. So for sound, we talk about the intensity level. Now, we have to be clear. The intensity level is not the same thing as the intensity. Okay, that's what this whole bit is about. The intensity level is represented by the Greek letter beta, and it has units of decibels. So, aptly named after Alexander Graham Bell, who did so much work with sound and the telephone and everything. So, when we're talking about intensity, we're talking specifically about power per area, watts per meter squared. When we're talking about intensity level, we're talking about decibels. Now, this gets a little tricky because the decibel is effectively the loudness. And we talk about it in terms of how we compare it to other sounds. Now, are there sound waves that are emitted that we can't hear? There are. Does that mean it has zero energy? It does not. So just because it has a sound intensity level of 0 doesn't mean that it has 0 intensity. So again, this intensity level is about comparing sounds that we as humans can hear. And it turns out we're dealing with something called a log scale. So think back to Algebra 2 when you had to deal with logarithms. And basically the idea is that if I graph decibels versus intensity, if I graph my intensity level versus intensity here, I may have something that is, we'll say this is 0 on my decibel scale, 0 on my intensity level scale, and we'll go 0, 10, 20, 30, a nice linear progression. I mean, this is what we're used to dealing with. But a log scale means that on the y-axis, on the vertical axis, we may start with 10 to the 0. And the next one up is 10 to the 1, 10 to the 2, so 10 squared, 10 cubed. Now, in reality, this is looking at 10 to the 0 is what? Any number raised to the 0 is always 1. Okay, that's just a common principle that I expect you to know. Okay, anything raised to the 0 is always 1. So my very base level here is not even 0, it's 1. And it goes from 1 to 10 to the 1 is 10, 10 squared is 100, 1,000. So I'm going up by powers of 10. That's what it means to be on a log scale. I'm going up by some power. Now, the way this will look then is if I have something that is 10 decibels, that may have an intensity of 10. This is just a really rough example. I may be able to double my intensity level, but what that does to my intensity itself is multiplies it by 10. So if I triple my intensity level, I multiply it by 100. So the idea is it's not like I double my intensity level and I double my intensity. That's not how this works. If I double my intensity level, I still have a log scale to deal with. So I want you to kind of be aware of that. The way we represent that mathematically, let's see, is we say that our loudness, our intensity level, is equal to this 10 decibel multiplier. Okay, this always just sits out in front. It's just a multiplier by 10, multiplied by the log of the intensity over our baseline threshold intensity, and I'll explain that here more in a second. So something I need to point out. First of all, this is log base 10. This is not natural log. This is not base 6, base 2. It's not base anything else. It is base 10. So when you're dealing with your calculator, just be aware you need to be using the log function. Okay, not the ln, not the natural log function. The other thing I need to point out is this I naught here. What is that? We say effectively that, well, we'll put it down here. This I naught term is the human threshold of intensity that we can hear. So, in other words, it's the softest sound we can detect. And it is equal to 10 to the negative 12th watts per meter squared. Okay, so this is a constant. So effectively, it's really pretty simple to get from intensity into intensity level. This is a constant, this is a constant, this is a function. So all you need is your intensity in order to figure out your intensity level. And you can actually go back and forth. How do you undo log? If you know your intensity, how do you undo log? Well, it's base 10. So logarithms are basically undoing exponents. Okay? So if I wanted to solve for intensity here, I can, the first thing I want to do in my order of operations is divide by my factor out here. So I can say beta, so my intensity level divided by 10. That gets rid of that. How do I undo this log term? Well, I raise 10 to everything. So I say 10 raised to the power of my intensity level divided by 10 is equal to I over I naught. Okay, so this is how you undo log, is 10 to the log of whatever is whatever. Okay, and then from there you can multiply by 10 to the negative 12 and solve for I. Okay, so just this is a quick algebra refresher, but I do expect you to be able to go back and forth between these two. So just as a quick point of reference, I'm going to give you some intensities versus intensity levels for some common sounds. So we said that the hearing threshold that the intensity is 10 to the negative 12th watts per meter squared, and that converts to an intensity level of 0 decibels. Okay, so all of these are going to have, all of my intensities are going to be in terms of watts per meter squared. All of my intensity levels are going to be in units of decibels. So we'll say a whisper, we're looking at something like 1 times 10 to the negative 10th as my intensity, and that is an intensity level of 20 decibels. So notice I went up by 2 powers of 10, but I only went up by 20 decibels. Normal, well, let's go with the, let's go ahead and jump up to the live rock concert. We're looking at something like 1 watt per meter squared. And in terms of loudness, we're looking at 120 decibels. Okay, so you kind of start to see that it's hard to see the relationship between the two. The pain threshold, for humans anyway, is 10 watts per meter squared, and that's sitting at 130 decibels. So notice my intensity level went up by a factor of 10, but my loudness level, my intensity level, only went up by 10 decibels. So something to kind of consider. 1 decibel is like our minimum hearing resolution. And what I mean by that is it's the minimum change that we can detect in loudness. So if you were to hear two sounds, one louder than the other, this would be the minimum difference between them that you could actually hear. Anything less than a decibel, and you couldn't tell whether one was louder than the other. Also, as we saw, if we double the intensity level, in other words, if we double the intensity level, it's not the same thing as doubling the intensity. And it's really not even the same thing as doubling the perceived loudness. And that's where that gets a little funny. But if I go from 10 decibels to 20 decibels, that is indeed doubling the intensity level. And that does sound like a doubling in loudness. Like you might say this one is twice as loud as the other. But here's where it gets a little funky. If I go from 60 decibels to 70 decibels, that's clearly not doubling the sound, or the intensity level, but it actually does double the loudness. Like I might say, like in this case, that, I mean, the rock concert isn't causing me pain. If something was twice as loud as a rock concert, it would cause me pain. That's kind of the idea that we're talking about here. So really the take-home point is I want you to be able to recognize and manipulate this relationship between intensity level and intensity. I don't expect you to memorize any of this. I just want you to be aware that our perception is different than our detection methods when we start talking about energy and power in terms of watts and joules and things that we're already familiar with Physics 1. Okay.